We had an array of failed power circuits before we got one that works. I believe we went through 5 or 6 boards and a lot of power MOSFETs. And we have a video to show you real quick, sorry, of what will happen if you run too much voltage through too little of an SMA. This is the smallest diameter wire we tested with, running 24 volts from our battery. It burns up. So you have to make sure that you have the appropriate combination of both power and diameter. We'll now hand off to Travis Krammes, who will tell you about our alternative designs.
All right. We didn't actually just go ahead and choose one design immediately, start building it. We actually went through several different alternative designs first and analyzed the strengths and weaknesses of each. The first one that we looked at, which I was particularly fond of for a little while, was one which actually used a low temperature actuator. When SMA is being actuated, it actually has 2 different modes of actuation. The first is one that coils that SMA itself rather than contracting it, and that's done at a lower temperature, whereas the second one is the actual contraction. Now, this actual design uses the coiling, and it has significantly less strength overall because of the lower temperature actuation. And the actuation is incredibly difficult to control actually, because when the SMA actuates at a lower temperature, it wants to wind itself up kind of like a solenoid. This is essentially what it would look like. Our second alternative design is one that actually controls all the joints of one SMA. The SMA is actually run right at the tip of the finger, so when it pulls down and contracts, the finger moves down with it. And this one is a preferable design because it only uses one SMA, so you're actually using less material overall. And it controls all the joints at once, giving you more fluid movement. Now, it does have some disadvantages. It is harder to pull all the joints at once sometimes. If they lock up, they will actually stay in place and then suddenly drop down. Now, we were limited on actuators. We were not allowed to choose between which actuator to use for this design, but we did look at others while we were researching. And we had servos and stepper motors that became apparent were used in other designs. The advantage of servo is that it uses fairly low power, actually, only about 6 volts, and has relatively fast actuation, about 180 degrees in 1.5 seconds. It also has a lot of little parts that break, though, which is a disadvantage, because when they break, it's usually a gear or something that strips, and you have to replace the servo itself. Now, stepper motor basically uses internal magnetism to turn the little arm there. It turns into slow increments. Now, the advantage of this is that it has excellent torque. It turns a lot of strength, but its disadvantage is that it actually uses pretty high current to operate, and it can be noisy at higher speeds. Now, overall, the SMA seems to be a better design, though, because it is just as fast as servo, and it's actually more durable. Also, it's solid state, so that when it contracts and expands, it doesn't have any strange little gears that can get snapped. Overall, our design itself was 5.6 pounds. The SMA is only a few grams. And for an entire 90 degree of actuation for our design, you need approximately 1 meter, but you actually have a very small volume with the actual wire. Now, we do have some disadvantages, of course, to any design. Ours actually saw a lot of current, about 6 amperes. That's pretty massive current, actually, all things considered. And the SMAs, of course, require heat to contract, not electricity. So not only are you dealing with high voltage, you're dealing with high heat, which is, of course, dangerous to human beings. Now, we did have a lot of advantages, though, of this design. For example, it's easy to expand the control system. You can actually port a multiplex from the microcontroller, so you only need 1 microcontroller overall to control 5 fingers. Switching the circuit is actually very simple. You can implement it many other times, and you can expand it to include many of the joints. And only 1 SMA is actually used for each direction of actuation. It's a fairly simple design that way. The LCD and keypad are very good for testing purposes. You can input your speed, you can input an angle over that, and you can change the angle mid-use. The circuit itself is also relatively cheap. It's on the order of $10 or so. And like I said earlier, it's solid state, it's not a gearbox, so you don't get stripping bearings. Total cost, though, for this guy was about $426. A little bit high. Now, before I go into some questions, would you guys like to go ahead and start up a demo?
We're going to do a medium actuation at a 45-degree angle. It should actuate and stop at 45 degrees and hold its position. Here we go. And we're going to go and change it to 90 degrees, and it keeps actuating. And that is our